Ok, donc je te propose qu'on commence, ça fera venir les derniers retardataires. Je vais faire une toute petite introduction en français et je te laisserai passer en anglais après ça. Donc aujourd'hui, on reçoit Frédéric Courbin, qui donc a une forte expertise sur les lentilles gravitationnelles et qui donc aujourd'hui va nous parler de ce qui peut être fait avec donc des outils de machine learning sur cette thématique. Donc Frédéric, pardon, j'ai pas précisé, donc qui est professeur à l'École polytechnique fédérale de Lausanne. Voilà, donc je te remercie encore d'être parmi nous, Frédéric, et je te laisse prendre la main.
Mm-hmm. Okay, so I will switch to English. So actually, I didn't know exactly what audience I would have here. So this will be a mix between lensing and machine learning, although you're probably all more expert than me in machine learning. So actually, I have a funny illustration here. This is called the horseshoe lens because it has a shape of horseshoe. And this is just to illustrate, the way we think we understand data augmentation. This is very obscure to me, actually, but anyway, so that was to illustrate, how to find lenses with deep learning. It's probably not the only method, and it's not, let's say, always necessary. Give a hammer to someone and all problems are a nail. And I think this applies to machine learning. So machine learning is desirable in many cases, but not all the time. And in terms of lens finding, it has many limitations. The main one being that if you're looking for lenses that are rare, of course, in a survey, you don't have examples to show your network in the first place. So you have to live with essentially simulated training sets. And this talk will be more about, so why lensing first, and then lens finding in DES and in unions, so Cephees originally, and while we're working on Cephees, this became unions. And then ultimately what we want is a lens finding pipeline for Euclid, since I'm deeply involved in the lens finding in Euclid. So this work is really a collection of different works by all these people, plus some input of the Euclid strong lensing science working group. Okay, so I thought, first, so I don't know how many of you are familiar with lensing, but this is how it works and how it shows. So you have here a number of lenses, which are very different. So they are all, of course, produced by GR of a potential well, and the potential well is the one of the lens. In all these cases, we have strong lensing. So why strong lensing? Strong lensing because you have multiple images of sources in the background of foreground lenses at galaxy scale. So strong lensing can occur, of course, at different scales. I will show this a bit later, but we focus for lens searches on galaxy scale strong lenses for many reasons. There are many things to do with these in terms of astrophysics and cosmology. And the other reason is that they are by far the more numerous on the sky. So that's really the category of lenses you really don't want to miss in Euclid, for example, and in LSST or in any survey. So just to give you examples of the fauna of strong lenses. So here is one. Actually, that was discovered some time ago. It's a very lucky one where you have a lens and two sources at different redshift lengths like this. So that's called a jackpot lens because it's very rare. And you have here an Einstein ring. That's the area where you see the lensed images of one source in that case. And then you have another source here at a different Einstein radius. And these lenses are super nice because you can constrain very well your lens model thanks to the two sources at two different redshift. And you can even measure ratios of distances between you and the different sources and the lens. And in the end, do constrain cosmology with this, essentially measure H0. So that's one type of lens. Another nice thing is that lenses are not necessarily isolated. They live in groups. So you see here a lens, different companions, and the companion here that falls on the lensed image produced by the rest of the potential well. And you see image splitting here by this galaxy G4. And that's super powerful to detect substructures to lenses. So if that's the lens, G2, G3, G4 can be considered as substructures. In this case, you see the substructure, but in many cases you don't see it. So it's an indirect way of probing galaxy subhalos thanks to lensing. In some cases, you have spiral lens galaxies. That's a face on one, an edge on one, where you have 1, 2, 3, 4 images of a background source and its host galaxy that you see as an Einstein ring. Actually, finding lensing by face on spiral is super hard, just because in terms of machine learning, spiral arms mimic the lensing features. So you end up with samples with tons of false positives. Now they are there on the sky. We'll have to find them somewhere, somehow. Now, a nice thing in this specific case of edge on spiral is that you can do a rotation curve of the lens, and you get the detailed mass, the very precise total mass, so visible plus dark in the Einstein radius, and then you constrain very well your lens model in combination with the dynamics. So these are also very useful lenses. Another type of lens is where you have a lensed quasar. So there you have 1, 2, 3, 4 images of a quasar. And this ring is its lensed host galaxy. And this is the lens galaxy and some companion to it. So another substructure, you would say. And in some very rare cases, you also have lensing by quasars. I will show why this is useful later. So there you have a quasar that is merging with a galaxy at the same redshift, and that produces images of some more distant galaxies. And thanks to this, you can measure the mass of the main lens, of the quasar, and its host galaxy. So I will detail more this specific object later to show you why we should look for more of these cases. This is the only known case of a quasar acting as a lens, actually, for now. So anyway, so you already see that the diversity in lenses is huge. Diversity in application is also huge. So I won't review everything in this talk, but this is to give you an overview of what you can do in essentially all area of astrophysics, from cosmology to galaxy formation and evolution to physics of quasars and black holes. You can image very distant galaxies, so study the early universe, because lensing is a natural telescope. It distorts the lensed images, but it magnifies them. So it gives you, not that it gives you more flux, but it stretches the images of objects on the sky and make them brighter as they are in reality. And the light of the different images to you pass through the lensing galaxy and through its interstellar medium. So you can probe the AGM and the ASM in lens galaxies and between members of groups that act as a lens, for example. So I will, just to show a few examples, I won't speak of weak lensing. That's the whole point of Euclid, for example, that will map all the distortions of all galaxies on the whole sky, or close to this. So, lensing that was kind of a curiosity some time ago is now the main cosmological probe of many surveys, so including Euclid and Rubin and LSST. You can measure H0 with it, with lensing. I will show examples of that. You can measure the mass profile, so total mass of galaxies, groups, and clusters. You can, in some cases, address the core cusp problem in the center of lens galaxies. You can study quasar host galaxies, either because they lens something in the background, so you can measure their mass and measure the mass profile, or because they are lensed by something, and then you see the host galaxy of distant quasars that is stretched outside the area where the quasar is. So you immediately have access to the host galaxy. So it's not that you have a coronagraph, let's say, but you see the host galaxy bigger than it is, and then it's not contaminated anymore by the quasar. This I will focus a bit more on in this talk. So how to address the problem of missing satellites. It also addresses the problem of whether the dark matter is cold or warm. And in the micro lensing regime, so lensing of, let's say, sources by stars, so that's called micro lensing. You can study, you can even measure the accretion disk, the energy profile of quasar accretion disks, and study the broadline region in the same way. And you can do quasar galaxy coevolution when you use quasars acting as lenses. So okay, so that's this list is of course incomplete, and I won't describe everything there, but just wanted to tell you, give you a taste of why we should worry about lensing, and in particular strong lensing at galaxy scale or quasar scale. So an example I like, an application I like, I've been working a lot in this field, is when you find lens quasars, you can measure time delays between the arrival time of photons to the observer, or let's say between the lens images and the observer. So let's say if you have a signal coming from a variable source, a quasar or a supernova, so this is lensed, you have different paths to the observer, so different lensed images. And then the thing is that because of two reasons, first because these optical paths are not the same, and because the potential well of the lens galaxy here and here is not the same, photons in one path are delayed with respect to the other. And this is the time delay. Now, this time delay depends on the potential well of the lens and on the geometry of the system. So if you have a model for the lens, you measure the delay, you measure the geometry of the system, you potentially have H0 because this delay is inversely proportional to H0. And just qualitatively, if you have a large universe, you have a small H0 and a large delay. In a smaller universe, the delay would be shorter and then H0 is larger. So that's the principle of the method that was proposed by Schur-Efsdal back in 1964. So how you measure the delay? I show an example here. Let's see if it works with Zoom. So you accumulate photometric data for the different lensed images of your quasar. So you see maybe the flickering of the images here over the years. So of course, we don't do this with HST, but this is just to illustrate. And what you see here is that the different images vary with time. They look alike. They are contaminated by microlensing by stars passing in front of each quasar, but overall, you can see that you can find a shift between pairs of images. So let's say image 1, 2, 3, or let's say A, B, C, don't have a delay visible by eye on this image, but the longer delay between image D and the others can be seen by eye. So for example, here you have a bump, and you have the same bump here 90 days later in the image D. So, okay, so you measure the delay, you have a lens model, measure H0. Why would you do this at all? Because of the H0 tension. So no idea if you all know this, but I thought I would give a reminder in one slide. So why would you want to measure H0 at all? Some will tell you, okay, we don't care, we don't need this to do astrophysics. But in terms of cosmological, it's super important. So how do you get H0 from lensing? I told you. And you measure H0, of course, at redshift 0. That's where the H0 measurement falls for lensing and supernovae. And you can also measure, so that's a local measurement of H0. Everything is at low redshift. Even high redshift supernovae at redshift 1, 2 are still very low redshift. So that's a late measurement in the late universe here. And you can measure this with Planck. So with Planck, you in fact measure H of Z equal 1100, and then extrapolate it back with a cosmological model to redshift 0. And if you do this, you fall here. And these 2 points are not compatible currently. So that's the Hubble tension. And the interest of that is the problem is that the problem can be in the measurements. So maybe these measurements are wrong. Maybe this measurement here is wrong. Or maybe the curve that goes from this measurement to here is wrong. And that's the most interesting case because the curve is the cosmological model. So if you want this curve to go through this H0, you need to change cosmology. And that's the points h of z different from 0 from the BAO and so on. So thanks to lens quasars, you can constrain cosmology and address this Hubble tension. And for now, no one has the answer to that. And people have opinions, really marked opinions, but I think so far no answer. Okay, so that's one application. In terms of, I want to show this because that's how we measure our delays, by monitoring lens quasars. And we do this, among others, with the VST, so the VLT survey telescope at Paranal. And we have a large program, 2,000 hours over 2.5 years. And every day we expose for 30 minutes in there. Seeing is excellent. The total field of view is around 20 square degrees in total. And we obtain light curves for all our objects, so lens quasars, of course, that we put in the center of the field, but there are many other things like this, just AGNs that were not known. We discovered them from variability, supernovae that we catch from day 0, variable stars. And of course, so why I show this is first because this is data that are in fact better than LSST before LSST on a small field of view, 20 square degrees, but also because in terms of light curve classification, it poses challenges. That I must say we didn't address at all for now. We focus on lens quasars. We're also after lens supernovae using the same data. But I just wanted to illustrate because what we have here, we have like in our fields a few thousand variable objects in only 20 square degrees, not mentioning transients. So you can imagine what it will be with LSST. More or less with the same depth per epoch, except that LSST will have 8 times less points in the curves that we have here. Another application, probing dark matter. So of course, cold dark matter that predicts that galaxies form in a hierarchical way. Small things form bigger things in the late universe. And that's a snapshot of one of these I draw. Actually, no, this is a dark matter only simulation. I think it's just the millennium. No, it's not the millennium, actually. This is Eagle. So it's indeed an hydro simulation. In cold dark matter, you see many more clumps than if the dark matter is warm. So you form less structures in warm dark matter. This is zoom in the central area. We have where you have the projected mass. And then if you plot the power spectrum of this in CDM and WDM, you have different things after you pass some mass that is around 10 to the 7 solar masses. So at 10 to the 7 solar masses, these clumps are usually dark. So you don't see them, but lensing can see them. So we'll show you how. But why you do this in the first place? Because if you sit here, you know that, so if you count these structures at 10 to the 7 or even 10 to the 6 solar masses, so really tiny things that you don't see, especially at high Z, then you can discriminate just by counting these things between warm dark matter and cold dark matter. Now, how lensing does that? So I show here an example of 2 types of lenses. Essentially, in the universe, you have a lensing of extended structures, galaxies, and you have lensing of point sources like quasars. In fact, quasars are in galaxies, so you see a mix of these 2 things. Now, how small structures interfere with the lensing. So that's the illustration. You have a lens galaxy, you have the lens features, but if you have dark clumps in the lens or along the line of sight, then you will see perturbed images. These are tiny distortions, I exaggerate here. But that's how you can spot dark substructures along the line of sight to lenses. Now, if you have lens quasars, in the absence of substructures, you would predict given flux ratios between the lensed images. Of course, that varies with time, so you need to measure these ratios to measure light curves, correct for the time delay that I showed before, and then divide, then you obtain, in principle, the flux ratio between these images. Now, if you have substructures lying next to these images, these flux ratios will become anomalous. And you can know, if you have a sample of lens point sources, how many black things you need here and how close to the images and how concentrated they are. So you can measure this with a sample of lenses with anomalous flux ratios or with thick rings that have distortions due to these subhalos. So just to show you examples, so this one I showed you already. So that's a gravitational lens, and then you have this satellite that is luminous in this case. It's a massive one that produces such a distortion, but in many cases you just don't see this at all. So here I have a simulation of an HST image of a ring, and we put a substructure here, a dark one, 10 to the 9 here, solar masses. And what we do, so we just do an experiment, that's a simulation. Thanks to automatic differentiation, we can compute the derivative of each pixels in the light with respect to a change in the mass map of the lens. And that gives you some kind of sensitivity map across your field of view. And where you have a spot in this sensitivity map, you know that there was something affecting the lensed image of the source. So that's one way to detect small substructures, and even you're sensitive to their concentration. You see here the substructure was injected as a single isothermal sphere, and here as a narrow Franken-White profile. And you see that you don't have the same sensitivity. So, okay, let's say you have a way to detect these halos, and actually there are machine learning methods being developed to produce these sensitivity maps. That's a whole field starting now. I'm not doing this, I'm doing more, fitting models in maybe in a Bayesian way, but not with machine learning. But that's just to tell you that this is really fast developing. And why? Because we'll have many lenses in Euclid. And there, okay, I show you, okay, Euclid or whatever survey, you need high resolution images to do this. So Euclid is better to do this kind of project. You have a lens source and you have the lens galaxy. Maybe it has a substructure in it, or it has a substructure along the line of sight in projection in the lens plane at the position of where it would be if it was in the lens galaxy. So that means that if you see a substructure at some position here, you don't know if it's in the lens plane or if it's on that line. And of course, the mass sensitivity changes there. So that's the complication. The advantage, on the other hand, is that you become sensitive to this whole volume that is populated by substructures. Well, let's say substructures is rather when it's in the lens, and line of sight halo is when, well, it's on the line of sight. So of course, subhalos in the lens are rare. Line of sight subhalos are numerous. So I skip all the step on knowing where the subhalo is. That's also a hot field at the moment. I'll just give you some statistics. So you remember at 10 to the 8 solar masses, CDM and WDM are more or less the same in terms of power spectrum of the dark clumps. But at 10 to the 7, you have many more substructures in cold dark matter than in warm dark matter. So these numbers here are the number of halos anywhere there in some cone or truncated cone, I don't know how to call this. So that's the number of halos you find per square arc second on the sky. So if this is 1 arc second, you will find 0.4 halo somewhere in this volume in CDM, and 0.1 halo if it's warm dark matter. And at 10 to the 7, of course, the difference between the two is larger, and that's where you can discriminate between CDM and WDM. So you can do this for lenses where the source is a galaxy, usually not at redshift much beyond 1, 1.2. And for quasars, you have longer lines of sight, which is why the number here are bigger. Now, the number in parentheses are the numbers if you have 30,000 galaxy scale lenses, and if you have 1,000 lensed quasars. And you see these numbers are huge. So you probe potentially 10,000 halos in cold dark matter here and 100,000 halos, in cold dark matter at 10 to the 8 solar masses, and like 100,000 at 10 to the 7 solar masses. And there you can discriminate with good statistics between CDM and warm dark matter, provided you detect them with lensing. So you see, you pass from, if you have a few lenses to play with, these are the numbers you have to use. If you have 30,000 lenses with Euclid, and we will have them, and that's also why we devise method to find them, these are the numbers we will have. Okay. Another reason to find lenses, they are cosmic beacons. So I like this object because we discovered it some time ago. I have only one slide on that, but I really wanted to show it because it's a super jackpot lens. So here you have a lens galaxy, and you have 1, 2, 3, 4 images of a background quasar, and that quasar happens to be a physical binary. And the second quasar at the same redshift is here, and is doubly imaged. So you have 2 images of one quasar, 4 images of the other quasar, the host galaxy of one of them. This bluish thing is another galaxy at a different redshift, so that's super useful to constrain the lens models. And on top of that, since binary quasars live in special environments, overdense, we have the chance that the line of sight to the 2 quasars intersect the proximate DLA. So that makes this object super special. And there will be many more like this in Euclid, of course. But you have to find in the first place the lens quasars. So lenses act as cosmic beacons. If there wouldn't be a lens here, maybe you would see your proximate DLA, but there would be only one line of sight intersecting it. Now here you have 4 lines of sight. So that's really an exceptional object because for now we don't know that many of them because of no surveys to find them, or no high resolution and deep surveys. Euclid should find many such things. Then another type of rare objects. So for example, lensing by quasars now. So how to find this? So you take spectra of quasars. That's the line here. That's from SDSS. You have the spectrum of the quasar in black, but you also have a set of lines, these red things, that correspond to a galaxy behind the quasar. So you know that within the SDSS fiber, there are 2 objects, the quasar and something behind, and you even have the redshift of these 2 things. So then you go to imaging, you go to Keck and you obtain this. So quite disappointing. That's the quasar, and there are stuff around, but nothing convincing. You use image deconvolution, potentially with machine learning. This was not done with machine learning. You go to your colleagues and say, oh, look, I found the ancient ring and so on. And the colleagues, of course, tell you, oh, no, this is probably deconvolution artifacts. Then you go to HST, and that's what you see. So that was done after that, actually. And then the model, to model this is super complex because you have a lens galaxy, the main one. You have a quasar at the same redshift. You have a companion at some unknown redshift. And you have lensing features. So why is this important? So first, for now, we have only 3 such cases. Only one is clear. That's the one I showed you. This one is very hard to model. And this one is really has a tiny ancient radius. Now, you can model the whole system. And what we show here, so we have the data minus the lens source that is here. That's for our lens models, and that's the reconstruction of the lens source. You can do the source reconstruction parametrically or non-parametrically. And in the 2 cases, when we change the mass of the quasar here in the model, we find a minimum at the same place, whatever we do with the different types of models, and that's 10 to the 10 solar masses. So it means that with this object, we can get the mass of a quasar that is a substructure of another lens galaxy. So fine, it's a special object, looks pretty, but is it useful? And that's why it's useful. So you all know the mass of the host, mass of black hole relation, the scaling relation from Cormendi and others. This is the relation for really nearby AGNs. really, really nearby, almost redshift 0. So of course, it's super hard to measure the stellar mass under the quasar. In our case, we get the mass to 1% in some aperture, which is the Einstein radius of the quasar. And we can put our point here. So we have only 1 point for now. So there, the blue points are the total mass of the main lensing galaxy. So remember, main lensing galaxy is that one. And the host galaxy of the quasar is the thing you don't see here under the quasar, but we get its total mass. So the total mass of, sorry, the QSO host, yeah, is here. So falling on the relation. Oh, it's only 1 point, but okay. But it means that, you know, before you needed to establish this relation to measure the stellar mass, which is extremely hard. So you can't do this at high Z. Measuring the black hole mass, okay, you have the spectrum. So in each case here, you can measure it if you have access to the correct wavelength range. You can also do this relation with the velocity dispersion of the host, but you have to measure it again, or with lensing. And lensing gives you, again, the total mass to 1%. You see in this plot, the horizontal axis doesn't even have an error bar. You know, it's extremely precise. There is a lot more uncertainty on the black hole mass. So why this is important? Because Euclid should find around a few hundreds of these objects. So it means we can have the scaling relations for quasar-host galaxies, not only at redshift 0, but at higher redshift, and maybe its evolution with redshift. So you see again, you know, another reason for using lensing to study, you know, quasar galaxy coevolution through the scaling relations. Now, okay, you have to find the lenses. So that's the sample, the SLAC sample. I don't know if you know it. It was also found with spectroscopy and then going to imaging with HST, and that's the type of things you find. And that's, you know, this sample, probably one of the most famous sample of lenses so far, has been, you know, this is the result of years and years of data collecting and modeling and so on. And that's what you expect in Euclid. So that's years of work. That's 2 months of Euclid operations. So that's the kind of numbers we have to deal with. Just for galaxy scale lenses. So what we did now, so what I will show now is the results we have in Cephis and DES. So we use, in fact, no, since we don't have the we don't have any Euclid data yet, we use Cephis and DES as test bench to explore the diversity of lenses. We have to define what pre-selection we do. We can't inspect even with machine learning all the lenses. So we have also, you know, DES has color, Cephis has resolution. So we could compare the two surveys. Actually, we find that resolution is really key. So that's good news for Euclid. So resolution is better. It's better to have high resolution single band images than color images. We want to build catalogs of contaminants on real data to find lenses in large numbers to already follow up the lenses. And then when we get Euclid, we'll already have a sample of real lenses that have been followed up from the ground. And we want to test modeling tools, want to test deblending tools. And eventually, I think in Euclid, what we will want to do is to drop training sets that are fully simulated or partly simulated and use only self-supervised learning or unsupervised learning using real Euclid images of real lenses. But for now, no, there are too few. Well, for now, there are none, but there are not even enough lenses that we could use if Euclid observed them all to do machine learning. So one method to find lenses is brute force. And we did this back in 2014. So brute force means we essentially downloaded the whole HST archive taken with the ACS in the red filter. So that's 7 square degrees, and we inspected everything by eye. So that was a bit painful, but that leads to nice estimates of the prevalence of lenses on the sky, and also gives an idea of the, let's say, the diversity in lens types. So you see here, for example, you have 1, 2, 3, 4 images. Actually, that's a candidate. It's not a confirmed lens. but potentially you have 4 images of something lensed by a low surface brightness object. So you don't expect that. So essentially, if you do simulated training sets, you won't simulate such things. You can have extreme magnification here of objects. So you have to know that these things exist at all to not to simulate them. You have objects that are really problematic for machine learning, where here you have an edge-on lens, something like a ring behind and tons of companions there, and that's usually, that would be probably classified as a false positive by CNNs, or things like this, where you have a merger and rings here that are lensing features. Now, another nice thing with this brute force test is that we could evaluate the number density of lenses per square degree as a function of depth. So that's HST AB magnitude that corresponds to, and Euclid falls here in this system. Now, these are our points from our visual search. This is the number of lenses in Cosmos that were not evaluated by us and that still fall on this curve. And this is where Euclid should lie in terms of depth. Then if we rescale our 7 square degrees to 15,000 square degrees, we find that we should find at least 60,000 galaxy scale lenses in Euclid if we were going to inspect everything by eye. Of course, we won't do this, and we'll use machine learning. And there, the first problem is even just stupid things like how to choose stamp size and how this will affect your search. So here you have many different configurations. You have a non-lens, NL is non-lens. Here you have a lens. Okay, these are clear cases. But then you have things that could be, if you have a small stamp size, this could be identified as a lens potentially because you have 2 objects. CNN could very well learn this as a lens. In fact, it's 2 non-lenses. If you work at the catalog level to extract your stamps, there is a risk that you will extract, in this case, for example, 5 stamps centered on each of these objects, and maybe all will be identified as a lens, or maybe not, depending on how much of the rest of the system is clipped by the different stamps. So you see, if you have 2 searches using deep learning with different stamp size, I'm sure you get different results. A nice example is this one. Now, this is not a lens, the lens is here, but since one image is bluish here next to this reddish thing, then maybe this would be classified as a lens by a CNN. Another thing, obvious thing, that you can have lensing features falling outside your stamp, and then you have more complex morphologies. And here, okay, I just show you different examples. It can become really complicated, especially in clusters, depending on how the stamps are extracted at the catalog level. So it looks easy like this by eye, but for a CNN, this can be really, really puzzling. It also depends on what you consider being a lens. Maybe someone will tell you, okay, the lens is the whole cluster, so I want the cluster to be identified as a lens, but then you need huge stamps and different simulations than if you look for galaxy scale lenses. And then if you do that, again, your results will depend on the stamp size you have chosen. So that's a super simple problem that makes life very complicated. And that's valid for any deep learning method. So what we did in Cepheids and DES, so we start by pre-selecting the objects. So okay, I won't tell much here. We have a color pre-selection to select mostly LRGs, luminous red galaxies, 18 million in DES, 2 million in Cepheids. There are different, that corresponds to different areas on the sky and so on. We have different stamp size because anyway, the pixel size is not the same in the 2 surveys. But that's the way we select objects. Actually, an extra complication is that you have many different populations overlapping in color. So you have to discriminate between these thanks to the morphology. But you also have to account for the mix of red and blue colors when you see a lens, because the source is blue, the lens is red. So you don't want your pre-selection to select only LRGs because your objects are mixed with blue things, the lens features. So even that step is super complicated when you do a color selection. Of course, one option is not to do a color selection, but then you have to inspect all your objects in the survey. Okay, so we have different color selection in the different surveys. I mean, different selections in the different surveys in color in DES, but only we only have an narrowband selection in Cepheids with shallow colors of pan stars. So in fact, the two data types are quite different. Now, I told you we don't have enough known lenses to do self-supervised learning, so we do simulations. And to do that, we take objects that have colors of LRGs, and we paint lensing behind these objects. And we do the same in Cepheids. So it's kind of data-driven simulation. All the foreground and the lens is taken from the data, and the lensed features are painted, calculated, let's say, using I think we used the Cosmos field in this case to lens the sources. Okay, so you have the simulations, you find the lenses, and then you need to clean the sample of false positive, and there are many. I think that's really the limitation of all these searches. Here is a sample of real lenses we find. That's what we call maybe lenses. Now, there's a big issue already on how you define what is a sure lens, a maybe lens, a possibly lens. You can find all kinds of classification in the literature. Some authors, for example, will classify all these as lenses because there is a banana-shaped blue thing next to a red thing. We consider that this is only a candidate. You have ring galaxies, spiral galaxies, mergers. All these are contaminants. And for now, there are not enough of them to train neural networks against them. So that's another second issue. So we try to expand these samples using GANs, for example, to produce more of them and train against these objects. But for now, it doesn't work very well. And once you find a lens, some people will tell you, fine, fit a lens model. So you fit a lens model on this, it fits. Problem is that if you fit a lens model on this, it also fits. So to me, fitting a lens model on a candidate is not a proof that it's a lens. Now, for the visual inspection, so we take our CNNs, we take objects in DES with a given score, objects in Cepheids with another score. That's objects to inspect. So it's just to show you how we did this. We did this in two steps. Step one is we have a grid of 10 by 10 stamps, and we click on any object that can be a lens. And in a second step, we refine our selection and then classify the lenses as sure lens, maybe lens, flexion, so that this banana-shaped thing, and interlopers. And we also check that we are not influenced by the position of the object in the grid. So we are 6 different people classifying, and that's our heat map. So it means on average here, how many times we click on each stamp position in the grid. And each of the 6 users see a random realization of the same objects at different positions. So we are not biased like this, but we try to explore these kind of things. So it's not machine learning, but it's the visual inspection step. The big issue is that many different users don't agree on the different types of lenses. So that's how many users, how many objects each user classify as a sure lens, striking lensing features, or maybe lens, you're convinced but you wouldn't burn telescope time on this. And you see that we have all seen the same number of lenses, and that's of candidates, sorry, and that's the different numbers by different users. And not only this, but there is very different overlap between different users. Even though we had the training session where we agreed on what would be a lens, a maybe lens, and so on. So that's probably, after the machine learning step, the next big issue we will have with Euclid, how to remove these false positives, or let's say what lenses are more important than others that are just candidates. So we are not the only one who looked for lenses in DES, for example. Jacobs, in fact, started that. And that's an illustration on how we disagree on the visual classification. So that's all candidates that Jacobs considered as candidates that we found in our search, but discarded completely at the visual inspection step. So you see, each time the CNN score is high, 1.999 and so on. But in the end, I don't see any lensing, any trace of lensing there. Maybe in a few objects, maybe that one, maybe that one. There are also discrepancies between us and Jacobs due to the stamp size. So for example, there are things like this that are in fact part of a cluster. You remember that's the illustration I showed you before. No, maybe in Jacobs, where the stamp size was bigger, there was an arc outside the stamp and we don't get it. And still the CNN score is high. So that also illustrates the fact that we have no idea, in fact, of what the CNNs are actually learning there. Maybe it's learning the fact that there is something blue next to something red, and that's it. It looks like it learns the tangential distribution of light around the central object, but it does not discriminate between junk and lenses. Okay, so that was for the lens finding part. Now, if I see if we have lenses, we want to deblend the light of the lens and of the object. And for that, so we don't do this, well, we can do this with machine learning, I will show you later. But if you have color images, what we use is morphospectral component analysis. And that's how it works. You say that your data, so that's an image in a given band, one filter, the same object in a different filter, and you can add the filters here. And you say, my set of data is a mixture of the red and the blue channel. And how you mix these two channels depends on the SED of the object. So this is the SED of the object, of the blue channel. This is the SED of what you believe is the SED of the red channel. And then you mix this, you do a weighted sum of these two channels to reproduce each of the data. So great advantage, you can deblend things without a lens model. And that's the result. So here is, these are really good candidates that we have. And that's the deblended version. So that's the red channel, and that's the blue channel. You see that sometimes there are some residuals of the blue stuff in the red channel. So it's not perfect, but good enough, for example, to initialize a lens model to run on this. And in some cases, it works almost perfectly. You even see this red thing in between the blue images that is well separated. Okay, so that's an important step for the follow-up of your lenses. It's not machine learning, but you can use machine learning to deblend objects. So for example, if you have only one single band, you can't use the tool I was showing you before. So you have a number of lenses here. And what we do here is we use autoencoders, and we use the mapping between the inputs and the labels. So when we train, we show the network the lens sources, we show the network the LRGs, so the lens, and of course we show the data, so that's the input. And now that's not the training set, that's the result. We show the stamp, the data stamp, and that deblends it into what can be the lens source and what could be the lens index, and that's the residuals. So you see it's not perfect. For now, we don't manage to recover the high frequency signal because we don't have a big enough training set. But in principle, that's a tool to deblend lenses with machine learning with single band images. So we have, just because you have one single band, you can't use the standard tools. Actually, the morphological component analysis is not that standard. But here, in Euclid, we'll have only one single band. I don't count the infrared band because the resolution and pixel size is really worse than optical. But that's probably the kind of thing we'll use in Euclid, these images. Okay, so now quick word about the Euclid lens finding pipeline. So for now, there is no pipeline. There are elements that I just showed you. Now, what it will have to deal with is tiles of 32 by 32 arc minutes. That means 50,000 tiles over the full survey. And that's essentially, so what we'll do is to just have a magnitude selection. We'll take everything brighter than 22. That's 1,000 objects per tile. That's the number of lenses we expect from theory. But to remember the completely data-driven approach, the brute force search was saying around 60,000 lenses, which is not incompatible with this, given the low numbers we have, the low number statistics we have. Now, this means we'll have 3 lenses per tile. Euclid does 20 tiles per day. So it means we need to find 60 lenses per day among 20,000 objects to test. Now, the false positive rate is around 0.5%. Looks nice, but it's not nice enough, because that means 100 false positive every day that you have to inspect for 7 years of the survey. So how feasible this is? Now, if you have to do a few days, it's fine. If you have to do 7 years, it's another story. Okay, so now what we have with this search, so we don't try to do even science with these lenses for now. We just try to see how we can apply our methods to Euclid. Now, in the ES, using 18 million objects, we find only 405 sure lenses. The paper I showed you before of Jacobs et al. Find like 3 times more, but as you saw after visual inspection, a lot of them are not real lenses. In Cepheid, okay, we have a small area, smaller number of galaxies. If you scale this to this, you will see that these 2 numbers are approximately compatible. But remember that here we don't have the color information. We usually have better seeing than the ES. But overall, these 2 numbers are compatible. So we can consider that these will be the numbers we have to deal with in Euclid. Not the absolute numbers, but in terms of the efficiency of the CNN and so on. That's what we can hope for. Now, the quality of the training sets, that's a general conclusion that we have. We can use whatever network, the last fancy thing, super deep network. Everything in the end will be driven by the quality of your training set. And in doing this, you don't want to mimic nature. So you don't want to, let's say, have a training set that contains less of the rare objects and more of the more common objects. You want to sample this equally. And when we see, if we compare our Cepheid and the ES results, so of course we have more objects in the ES, but usually the fraction of objects we classify visually after the CNN as sure lenses is more important in Cepheid than in the ES. So that means that really, high resolution prevail, not really the color information, which of course is useful in terms of deep blending and in measuring photometric redshift, for example, for your lenses and sources. But in terms of finding, it's really resolution that counts and the quality of the training set, which is why we think of slowly, migrating from simulated training sets to data-driven one, fully data-driven one. So we have, okay, so in Euclid, we'll go for single band, no color selection, although we can use color afterward, after the discovery for follow-up. We have far too many false positives, 0.5% is nice. That's usually what you get with CNNs. Well, again, it depends a lot on the training set, but we'll have to improve on that. That will be the most challenging part of the job. And again, we want to go to fully data-driven training set. After 1 year of mission, we should have enough real lenses. If we find them with the trained networks, with the simulated training sets, sorry, then we should have sufficient number of lenses after 1 year to migrate to self-supervised learning or unsupervised learning. And of course, you see visual inspection plays a big role in this. So citizen science is something we are also starting to implement. And I didn't speak of the modeling step, but in the end, it's because it's not a big deal. 2 hours per lens, and we can improve this to half an hour. If we have to do 20 lenses per day, even a single laptop can do it. Actually, that's important because at the beginning of the project in 2011, we thought that this would be really the bottleneck. Okay, and I stop here. Thank you.
Okay, thank you very much, Frédéric. It was very interesting and in-depth presentation. So we have a bit of time for a few questions. If you can raise your hand in the Zoom to ask any question you can have. Okay, so we have one question from Norma. Norma, go ahead.
Hello. Thank you very much, Frédéric, for this, in my view, excellent presentation. And I would like to ask, have you results, no set prediction or prospective from simulations, but from your observations about discrimination or set testing water matter?
Mhm.
That's the first point. And
Yeah. So you mean prediction in terms of what?
About water matter with your observation, if you have already some results.
No, for now, no. Actually, there are lots of people on that now. There are papers, every week on new modeling methods to detect these things and so on where these substructures are along the line of sight or in the lens. But I would say for now, we know a handful of lenses where there is a detection of a substructure. And I think in only one case, we know that it's in the lens. In the other cases, it's not clear yet. And the main reason for that is the lack of high resolution observations, which is why I think, really Euclid is has a niche there.
Yes,
because it will have many lenses at high resolution. LSST won't do that.
Yes, because, with the HST and going to higher redshift, is much more, there is much more difference between water matter and dark and cold dark matter.
Sure.
And it can become really, factible to place the strong difference between both. That there are no such high number of substructures at the smaller scale, as you presented in your curves, which you show very clear the differences.
Yeah. So indeed, so now I showed just the simplistic picture of this, but of course you can go to simulations and see how many lines of sight subhalos you expect in warm dark matter, in cold dark matter as a function of redshift. Something I didn't mention at all, but that is important as well, is that these quantities probably change as a function of environment.
As a function, excuse me, as a function of
environment. If you have strong lenses in clusters or in filaments or in voids, you won't find the same.
But again, there is the work by Conselich et al. From already some years ago, that it makes that the environment as such, high redshift, is not so big as it was expected before HST.
It's true, but at high, actually, you want to be at fairly low redshift, because that's where you have between because before that, structures have not formed anyway in none of the scenarios. So
but
now the redshift range will be where we will have sensitivity is essentially lines of sight between 0 and around 1 for lens galaxies, and up to redshift 2 for lens quasars, because you see quasars further away.
And I don't know if there are some other questions, because I have a second one, but I don't want to monopolize.
I think you can go ahead if it's in just a few minutes, because I think Remy has a question too after.
Thank you. I find also interesting what you present about the scaling relations, and you said new scaling relations. That I mean, for the black holes and the coevolution of say the galaxy. I mean that you said new because what? Because of the redshift or
No.
and which mass for the supermassive black hole? Or I mean, yes, I refer to this slide.
So the new thing is, so mass of black hole, there is no change. It's just the same method as before.
Yes.
But
yes.
what you get is the total mass of the host galaxy, so dark plus visible. And not only you get it, but you get it to 1%. So that's the new bit. All these relations usually use stellar mass or stellar velocity dispersion.
Yeah. And that was known. That was known.
Well,
These two scaling relation for the stellar populations and so on, for the mass.
Yeah. That's what was done since maybe not forever, but a long time. But now lensing gives you access to this.
To the total mass.
Yeah, that's why I say new, because this was never measured before.
Yes.
Let's say it's somehow measured by sigma star, but then it's model dependent. It's here is just the total mass within the Einstein radius, which is you can do a model to measure it, but you don't even need that, because the Einstein radius is given by what you see of the lens source on the sky.
Yeah.
So that's the new bit. And it's not tracing the same thing as this, because this traces what happens to stars and the gas in the galaxy.
Yeah.
That traces what happens to the whole thing. So there may be surprises. It will be interesting. Actually, we have a project with Michaela.
I would like in this connection. I found it's very interesting. In this sense, for instance, we know that the total mass is also scaled with the size, and so you can have here some interesting relation about about the size for the black hole too, without without using any model for the black hole. I mean.
Yeah, that would be So probably lensing would not. It would get the mass of everything, the black hole plus the host galaxy, not the separate. You cannot discriminate between the two.
Yes, but we know that for the what have been measured for the galaxies, there is an scaling with the size, which, by the way, is connected with the surface gravity of the galaxy, which have been measured, and that is very interesting. And said you have. In some sense, you have also an scaling with the black hole mass.
Yeah.
Because
sure. There are lots of
the scaling between size and total mass of the galaxy hold for the whole system. Said the galaxy are all what because you cannot discriminate. I mean, if there is a black hole inside or not.
Yeah, because it's tiny compared to the whole galaxy.
Yes.
But that there is a whole lot of things to do there, because even in Euclid you will even see a bit of the host galaxy, so you can measure its mass, at least for the low redshift ones. I think that's a completely new field made possible with Euclid. Now it will never be huge numbers of objects. There was a paper by someone called Taak et al. Taak, who predicts around a few hundreds of such objects in Euclid.
Thanks.
But that's really nice.
Thanks. Yes, there are more. I mean, there are more things to discuss, but I mean, perhaps I will contact you. I mean, to do a presentation. I mean, for wider and for much more numerous audience. I mean, also for H0. I mean.
There is a lot of things to do, but to say.
Yes.
Yeah.
Very interesting. Thanks, Frédéric.
Okay. Well, thank you.
Okay, so for now we can.
And thanks, David.
No problem. Maybe we can take the question from Rémi.
Yeah. Great presentation. Thank you. It was very interesting. I have a few questions, but I think maybe we don't have time, so I'll be short. So you talked about at first that you don't know how you CNN detected the lens exactly.
Yeah.
Have you tried like, I don't know your CNN architecture, but maybe if you don't have too many filters, you could look at the filters and see exactly, since it's 2D images, you can see what features it extracts to the prediction.
Yeah, but it's kind of puzzling. What's, you know, it's hard to interpret, and so there are also these what's this called,
Saliency map. Yeah.
Yeah, and there, you know, one of my group to try that, and it's not super convincing, because, you know, you show a lens or a non-lens, okay, you essentially the saliency maps tell you that the CNN learned that there is an object in the image, essentially. And then it also depends a lot on the training. You know, at the beginning of our work, we had lots of problems with blue disky galaxies, and that's because we were simulating Einstein rings that were too small. So essentially, you know, we were simulating a red thing with a disky bluish thing. And then, of course, we had tons of false positives. You know, we were detecting all the all the high redshift disky galaxies just by changing one tiny thing in the training set.
Yeah.
So really, the training set is driving everything.
Yeah, and since you have so many types of lens, did you have some types that are easier to detect than other?
So we didn't really, let's say, no, what, so false positives are the problem. So of course, if you are going to look for arcs in face-on spirals, no, it will be a disaster, because you will detect all the spiral galaxies in the universe, and they will all be lenses for the networks. So now actually we have a project to detect lensing by edge-on spirals. One of the reasons is that, okay, it's interesting for science, but the second reason is that there are very few interlopers of that. You know, there is nothing else than an edge-on spiral that looks like an edge-on spiral on the sky. So indeed, yeah, different objects are easier than others. Now, the big difficulty in Euclid will be that we have, you know, essentially, we won't have any strong pre-selection of the objects. So there will be a mix of many different things, which will surely result in lots of false positives. So actually, it's true that we are wondering, you know, should we have several pipelines and so on? But if we have several pipelines, that means also several times doing the citizen science stuff. It's getting hard. But yeah, not all lenses are equivalent.
No, because with the equivalent, you can try to raise the learning set by making a few of them that are easier to detect, I think.
Yeah, but in the end, because we don't know what the network is learning, in fact, you show a lens and it's learning something else. And it finds all kinds of lenses you never simulated. So I think that's the main limitation of CNNs. You know, it's really the dependence on training set, and the fact that, at least as far as we are concerned, we don't understand what's happening in there.
And so you talked about GAN, so you try again to detect the lens?
Sorry?
When you use the GANs?
I know. So GANs are just because, so I was showing what, sorry. So it was when dealing with, so okay, so you find lenses, fine. And then you find all kinds of interlopers. The problem is that, again, next step is, okay, now we'll show these as negative examples to the network. The problem is that you have, you know, there are many of them, enough to be annoying, but not enough to train the network. So in the end, we end up by doing GANs to increase the data set of interlopers. That somehow works, but we saw that the network we use then to find lenses start to learn the difference between the real galaxies and the ones produced by GANs. No.
Because I know that GANs can generate discrete characteristic of your inputs. So you try GANs to get your results, not CNN. Well, you do use GAN to generate some inputs more. And
it was only.
And did you try the GANs to also detect what you want?
No, GANs for now. We just we just try to increase training sets. That's all. And it's not super. I don't know. Maybe we did something wrong, which is well possible. But there are lots of details. Like, for example, when we were simulating our lenses at the beginning, we had a PSF with a round support. There was a circular mask masking the PSF. And in some others, it was a square. And the network started to learn that.
Yeah.
And it's a stupid thing, and it's very hard to detect actually, because you convolve with the PSF and then add the noise. So this thing should disappear, and still not. So it's really strange that some CNNs are very efficient at detecting very subtle things, but sometimes come with crazy results on obvious things. Maybe just us, misusing the machine learning. But when we go to machine learning experts, usually, even here on campus, we have no top experts in machine learning, and we're hoping that they would come with miraculous solutions. No, you just said improve your training set.
Okay, thank you.
Okay, so any more questions?
Perhaps if there is time, just for a short point, but I don't know.
A short one, if you want. I have one or two questions afterward, and I think Frédéric has to leave very soon.
I have 12 minutes.
Yeah. But go ahead, Norma.
Oh, thank you. Just one point on the dark matter curve you show, and that you mentioned the difference about the in terms of the solar masses. Now, yes. Now, that depends to be precise. When because it's possible to do also high precision discriminations with HST and so on and others. To be precise, that depends also for cold dark matter on the value of the dark matter particle, which is not the case for cold dark matter. In cold dark matter, that is why it's cold. In fact, it's frozen because it's too high, because it's too high. Powers and power or giga electron volts, that for simulation and so on, that doesn't depend of the mass, explicitly of the mass of the dark matter particle, because it's taken like infinity set. Effectively, it's like it could be infinite. While cold dark matter, that is interesting point. Cold dark matter contains, as a particular case, cold dark matter in the limiting case in which the mass of the dark matter particle is going to infinity, because cold dark matter depends explicitly of the dark matter particle. And so you can also set that vary in a little range, because you cannot, that is why it's called cold dark matter. You cannot go to very, very light particles or to very heavy. And that also is an interesting point to, I mean, which with all this Euclid and your observations is interesting to trace. And with HST, it's possible too. Thank you.
Oh, yeah, sure. It would, actually, if you have different temperatures of dark matter, I can't draw anything strange. Okay, anyway, so, if you have a different mass particle, maybe the curve would be like this or like this. It evolved also with redshift. So,
and it could be, yeah, and it could be even some oscillations which appear, which will be interesting too.
No, sure. I mean,
in this part,
but for now we have only a few halos. So I think now it's really a matter of, actually, I think now what is more realistic is to challenge CDM rather than measuring, on which WDM curve we fall, because we don't have.
But CDM is very disfavored. I mean, from many others cumulative observations. So
it's true. But
in the strategy of discoveries, it's much interesting. I mean, to have positive measurements in some sense, or discoveries, and not
it's true.
Negative.
So actually, the quick forecast we have is that if we can detect 1,000 halos at 10⁷, we can discriminate between CDM and WDM at 20 sigma.
Very good.
But remember that for now we have 3 or 4 halos. so there is work.
Yes, with that I finish. But yes, in any case, it's interesting to know what all the other measurements, which are not in your observations and not with lensing, but with all other type of measurements, to see what happened and what are the constraints and the direction of data pointing out colder matter, because with that you can in some sense focalize better or interpret or doing your strategy. I mean, what I'm saying is also entirely valid for Euclid.
For what?
Euclid. For Euclid.
Euclid. Yeah, sure. Yeah. No, but there are many, here I just focused on a few things, but there would be so many. You can even lensing can even also address the core cusp problem. If you see my first slide.
The core cusp problem, very interesting too. And from that, if you take all the Gilmore and what he had from many years, and Walker and Worf galaxies. I mean, the cores are there.
There are no and even even the H knot problem. So I wanted to just show this because this is the horseshoe lens.
In some sense, there is no problem. In some sense, there is no cusp core problem, because you have because there are observations which show that the density, that the profiles are correct, and there are models which predict that the density profiles are correct, and so the problem is with those insisting in simulation which give a cusp, but that is the problem. I mean, it's not a fundamental problem. It was, but updating the subject, integrating all the observation, real data, I'm saying, not simulation, including Gaia. I mean, Gilmore analysis. And so that goes that there are cores, and the CASPET is really is not real. I mean, and that is also, it's also in agreement with I mean, what you find for the center of globular clusters, for the stars. There are no CASPET in density profiles in
that's
in
you know,
nature.
so some problems, let's say, are more, let's say, not alleviated, but let's say solved than others for now. No.
Yes.
I
Yes.
just picked here a number of problems that could be addressed.
Of course,
by
because
less.
I am speaking in this way because I know. I mean, there is an inertia in all fields, but I mean, I see with the type of observations and programs you are doing. I mean, is interesting. I mean, you can do in some sense. You can go in some sense beyond inertia.
Yeah, well,
Thank you.
You know, here the massive data may speak on their own, but for now we have nothing. And yeah.
Thank you.
Okay.
Okay, so I think we will stop here because you have to leave us. I would have had a lot of technical questions, but maybe I will write you an email about that.
Okay.
I think we can thank you again, Frédéric. Thank you a lot for this presentation and for your answer to all these questions. And I will say, I think we have our next seminar next week. I have to double check that, but no, we don't have seminar next week. So I will send everybody to the program of the seminar. Okay, so thank you again, Frédéric, and we will stop there. Thank you all.
Bye-bye.
Bye.